In the last video, we talked about the postulates of special relativity, the two postulates of special relativity. They seem fairly straightforward and simple, but their consequences are actually fairly significant. So let's talk a bit about two concepts. The first concept that we're going to introduce these postulates in is the concept of simultaneity. Simultaneity sounds a lot like the word simultaneous because it basically is the discussion of when events occur at the same time. So you have two events occurring in different points in space. When do we say they occur at the same time? Well, there are two ways of thinking about events at the same time. The first is, do we see the events at the same time? Or do we observe the events at the same time? Fireworks, if you go to the 4th of July, for instance, and if you see two fireworks go off in the sky at the same time, you might be tempted to say, oh, those events were simultaneous. The two fireworks exploded at the same instant in time. But let's look at it in a different way. That's not really what simultaneity means. Simultaneity means, do the events actually occur at the same time, not do we observe them to occur at the same time. And there's a slight distinction there that can be made a bit more clear if you have ever been in a thunderstorm, right? There's the old adage, count between the flash of lightning and the crack of thunder, and that can help you determine how far away the storm is. So the less time between the lightning and thunder, the closer the lightning was to you. And the reason that works is because the speed of light is much, much faster than the speed of sound. So when lightning strikes, we see the light almost instantaneously, but it takes a while for the sound of the thunder to reach us. The further away the lightning strike is, the longer the separation between the lightning that we see and the thunder that we hear. But this only works because the lightning and the thunder, while we don't observe them simultaneously, we see the lightning first and then we hear the thunder, we know that they occur simultaneously. The lightning causes the thunder, right? That's the source of the thunder, is the lightning bolt superheating the air. So, simultaneity is when events actually occur at the same time, not when we observe them to occur. So let's talk about the speed of light. Now, the speed of light is a constant in all reference frames. That's the second of Einstein's postulates. So, for special relativity. So let's do a thought experiment. And your book gives a similar thought experiment. I have one up on the board. We have two people. We have Rachel Red, shown here in red, and I believe Billy Blue, or Blue Billy, shown in blue. Now, Rachel Red here is on a train car that can travel at very, very, very high speeds, near the speed of light. So here's a train car. There's a box at her feet. That box is a special detector, which I'll talk about in a moment. And on either end of the train car, there are two large explosives, two fireworks, that when they go off, they give a big flash of light, and they scorch the ground below where they explode. So, this cart is moving to the right at speed v, which is a significant fraction of the speed of light. And Blue Billy is just sitting here on the side of the tracks watching Rachel Red zoom by. So, in this detector is special in that it senses which side sees the light from the firecrackers first. If the right side of this little box here, the detector, sees a flash before the left, the light will turn green. Otherwise, it turns red. So if it sees the flashes at the same time, the light turns red, or if it sees the flash from the left before the right, the light turns red. So the light will either be red or green in this experiment. Now, Rachel Red is standing in the middle of the flatbed with the detector at her feet. Two firecrackers are at either end of the flatbed, and they go off, they explode at the same time in Blue Billy's reference frame. So what color is the detector light? Well, in Blue Billy's reference frame, what we're going to see is right when Blue Billy is across from Rachel Red, the firecrackers explode. Boom. Now, the explosions give off light, right? So in the next step, so this is step one, the green shows a time difference. In step two, the cart is traveling further to the right. This is the light ray from each of the firecrackers. Firecracker was here, firecracker was there. the light rays move towards Blue Billy at the speed of light, and eventually, of course, they reach Blue Billy at the same time. Since the firecrackers were equidistant from Blue Billy, and the light travels at the same speed, Blue Billy not only sees the flashes at the same time, he knows they occurred at the same time because the fireworks are equidistant from him. So, Blue Billy, in Blue Billy's reference frame, the firecrackers do indeed explode at the same time. But what does the machine see? What does the detector, Rachel Ray, see? Well, Rachel, moving to the right at very high speed, passes through the light from the firework on the right, and the firework on the left takes a little while to catch up, right? It's traveling at, the light is traveling at the speed of light. Rachel is traveling at a slightly slower speed, so the light from the back firework does eventually catch up to her. But the machine clearly sees the flash from firework on the right compared to the firework on the left. And therefore, it says, right, the green, if the right side of the detector sees a flash before the left, the light turns green. So according to this experiment here, the light should be green. Well, let's look at it from Rachel Red's perspective. So she's just standing on this cart. There are fireworks on either side. And from her reference frame, Blue Billy is moving to the left at speed v, right? Just like when you're on a train, you see the trees whip by, you feel you're not moving, the trees appear to be moving towards you or past you. So Rachel Red isn't moving, Blue Billy is just sitting there. Fireworks go off, boom. What happens? Well, the light rays come off where the fireworks are emitted from the ends of the cart. And then eventually, those rays reach Rachel Red, it looks like the same time. Blue Billy, right, sees the light from the left firework first. The right one will eventually catch up. But according to what I have drawn here, it looks like the detector sees both flashes at the same time, which means that the light should turn red. Okay, problem. The light can't be both, right? It either saw the light from the right before the left and the light will turn green, or it saw them at the same time and the light will turn red. It can't be both green and red, right? When this experiment is done, and both Rachel Red and Billy Blue look at the detector, it's going to have a green light or it's going to have a red light. So one of these is wrong. This is called a paradox. A paradox is an apparent contradiction. And this is a paradox because we made an assumption here on the right. On the left, I said the two firecrackers either into the flatbed and explode at the same time in Blue Billy's reference frame. So what's on the left is correct. What's on the right is not. So how do we resolve this paradox? How do we fix it? Well, on the right, I assumed that the fireworks went off at the same time in Rachel Red's reference frame, right? They both blew up, the light rays moved with equal speed and hit Rachel at the same time. That's not what happens. From Rachel's perspective, what happens is that the firework on the right explodes first, then the firework on the left explodes. Here's the light from the firework on the left coming up. So the right side of this box sees the light from the firework in front, and then eventually sees the firework in the back catch up. So what we see is that events that are simultaneous in Billy Blue's reference frame are not simultaneous in Rachel Red's. Billy says the fireworks went off at exactly the same time. I saw them at the same time, they were equidistant from me, they went off at exactly the same time. And Rachel Red comes back and says, nope, this firework went off before that firework. The firework in front of me here went off before the firework behind me. And they were not simultaneous. Not that I didn't observe them at the same time. She did not observe them at the same time. But she knows that they were equidistant from her, so she knows they were not simultaneous. So is that a paradox? If Blue Billy says they were simultaneous and Rachel Red says they weren't. Einstein says no, it's not a paradox. You have relativity of simultaneity. Events that are simultaneous in one person's reference frame are not simultaneous necessarily in another person's reference frame. If they shared reference frames, they would have to agree, but they don't. One person is moving with respect to another, therefore they're not in the same reference frame. So that kind of blows your mind a bit. In Newtonian physics, if we say two events occurred at the same time, they occurred at the same time for everyone. Everyone in the universe would record the same events occurring at the same time. And Einstein said, no, that's not right. Because of the finite speed of light, the speed of light is the same for all observers in all reference frames, this is a consequence. Relativity simultaneity is relative. So that leads to some very interesting issues on how we measure time. And what we can say, what happens at the same time, what happens before, what happens after. So let's look at a concept called time dilation. Time dilation is a consequence of the fact that time and observers measure time differently in different reference frames. So time dilation occurs when you notice that an event moving with respect to you, the clocks or timing of that event occurs more slowly. So time is passing slowly for an observer who is moving with respect to another observer, or another way of saying that is moving clocks slow down. So in the room you're in right now, you can probably find a clock on the wall. Maybe you have an analog clock where the seconds just tick away. As you sit here, the time that occurs on that clock is at a regular pace. However, if you could see a spaceship fly by with that same clock on it, if that spaceship travels at an appreciable fraction of the speed of light, you'll note that the clock on that ship travels more slowly. It takes longer for those seconds to tick away than the clock in your room, because that clock in the spaceship is moving with respect to you. So when you observe the time between the ticks, the clock is in a different position in space every time it ticks away with respect to you, whereas the clock in your room is not, right? Every time that clock ticks away, or if you have a watch or a phone with a second hand, every time that second hand ticks away, your watch is the same distance from you. The clock on the wall is the same distance from you. So the event occurs in the same location in space, and it's not moving with respect to you. However, if I run by you wearing a watch, my watch is now moving with respect to you, and it would tick away a little bit more slowly. The faster you get to the speed of light, as the clock moves past, the slower the moving clock ticks away. Now this can be tricky to understand because you get weird effects, such as, since moving clocks travel more slowly, if I'm on Earth and I have a clock in my hand and I have a twin on a spaceship as they fly by at an appreciable speed to the speed of light, I would see my twin's clock travel more slowly. And that occurs for everything. Everything occurs more slowly. Biological processes occur more slowly. Nuclear decay occurs more slowly. The laws of physics actually, everything changes. Everything occurs. It looks like everything is running in slow motion compared to me. But if I were on the spaceship and looking to Earth, I'd see the same thing. If I were on the spaceship, everything would appear to be normal. And on Earth, everything would be ticking away more slowly because Earth is moving with respect to me. That's kind of weird. Each observer sees the other observer traveling more slowly. That's a bit, again, paradoxical, but that is what would happen. So I'm going to put up, rather than drawing up the derivation here, there's an image from your book that I'll show. It shows an event occurring in a spaceship where you have light. You have a little detector that shines a beam of light up, reflects off of a mirror, and it comes back down. So in the figure on the left of the two figures shown, the light beam, the observer has the detector at their feet. They see the beam of light emitted, it bounces off the mirror over their head, it comes back down, and is detected by the same device that emits it. So it's detected and emitted at the same location, at the observer's feet. So how fast does that little ray of light travel? Well, it travels at the speed of light upwards, bounces off the ceiling, comes back down. So whatever this distance is, the height of the spacecraft, I think your book uses d for the distance, it has to travel twice that distance. Right? It goes up d and then down d in some time t. And we know that time has to be, how long it takes depends on the distance of the spacecraft and the speed of light. So I can calculate the time between the events if I know what the speed of light is, and I do, and I know how far the light beam had to travel. Now that's for an observer in the spaceship. What if you're looking at the spaceship from Earth and you see the spaceship fly by? Well then, when the light beam is emitted, it's emitted in a different location than when it's detected. And this is the figure on the right now. So from the perspective of a person on Earth watching the spaceship fly by, the light beam is emitted, travels up at an angle, reflects off the mirror, which is now moved, bounces back down, and is detected by the detector again. It forms a triangle. So again, how fast it travels, well, depends on the speed of light, but we know the speed of light is a constant for everyone. Depends on how far it's traveled, and notice that the path it travels in the moving spaceship is a lot further than the path it travels in the stationary spaceship, because you have the hypotenuses of those triangles rather than just a straight line up and down. So if you calculate how much time it takes, you'll see that the time is actually longer. It takes longer for that event to occur in a moving spaceship than in a stationary one. If the spaceship is moving with respect to the observer versus the spaceship being stationary with respect to the observer. Same event, measuring 2 different times. That's time dilation. And the equation for that is given here. So the time measured in the moving spaceship that's moving with respect to the observer, is equal to what's called the proper time, delta T naught. This is the time between two events. The proper time is the time measured by an observer at rest relative to the event being observed. That means, at rest means that the event being observed doesn't move with respect to the observer. So for the person sitting in the spaceship, the device always stays at their feet. It never moves in space. So the light beam moves up and down, but the detector and emitter just stay in the same spot. For the person on Earth watching the spaceship fly by, the detector, it was emitted over here, the light beam bounces up, it comes back down. The detector has moved in the course of those events. So that's not the proper time. So the proper time is what you measure when you look at your watch. Your watch doesn't move with respect to you, so you're always measuring the proper time with a measuring device that stays stationary with respect to you. So if a device is moving, where the speed here, v, you plug in the speed. Now, so we know the speed of light, 299,792,458 meters per second. I can plug that in, and I can plug the velocity in at 10 meters per second, 20, 30, a million, whatever. Or I can put v in terms of c. I could put the velocity is 0.9 c, or 90% the speed of light, or 0.5 c, 50% the speed of light. And I can plug that in and calculate an event that takes 1 second or 1 hour in the proper reference frame will take longer in the moving reference frame. How much longer? That's what this equation calculates. You know, if there's a square root here, when v is 0, what happens? When v is 0, that means the object isn't moving with respect to us. It's stationary. So we should get the proper time out. Let's see what happens. Plug in 0 here. 0 over c is 0. 1 minus 0 is 1. Square root of 1 is 1. The time is equal to the proper time. Not surprising. As v approaches c, what happens if you hit the speed of light? Now, nothing except for massless particles can travel at the speed of light. Let's pretend the observer is traveling at the speed of light, or the spaceship is traveling at the speed of light. Well, then you have c here. The velocity is c. C squared over c squared is 1. 1 minus 1 is 0. We have a number over 0 that's basically undefined. It approaches infinity. As the speed of light approaches c, this time dilation approaches infinity. So this term, 1 over the square root of 1 minus v squared over c squared, is so common in special relativity, we give it its own term called gamma. Gamma is called the Lorentz factor. It's between 1 and infinity. For an object that's not moving, gamma is equal to 1. For an object that's moving very, 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 very close to the speed of light, gamma approaches infinity. So think of that as a multiplication of the time. How much slower is time traveling as an object approaches the speed of light? So that's this equation again. If you know what gamma is this term. So the time measured in the moving reference frame is equal to gamma times the proper time. Now, we've done experiments. Your watch is not precise enough to see, and we don't travel in our everyday lives, we don't travel close to the speed of light. So the time dilation that Einstein talked about was very difficult to initially measure when he first came up with it. But since then, we have created atomic clocks that keep ridiculously precise time. And we have airplanes and satellites that travel in space. We've measured this time dilation. If you have two identical clocks that are perfectly synchronized, two identical atomic clocks, and send one in a spacecraft or in an airplane flying around, moving, and then bring them back together, they read different times, slightly different times, because they're moving with respect to one another. So we actually have measured time dilation in the lab. We've tested Einstein's theories for the last 112 years now, and they've been shown to be time and again correct. Now then your book goes on to talk about an interesting phenomenon called the twins paradox. The twins paradox is that if I have an identical twin and I get on a spaceship and fly to a nearby star system and back, let's say Proxima Centauri, about 4 light years away. If I travel 4 light years at near the speed of light and back, I will have aged only weeks to months, depending on how fast I'm traveling. My twin will have aged 8 years. Because time travels differently. Now, I did say before, well, if each observer sees the other one as moving, don't both clocks slow down? Yes, initially, but one of the observers is also accelerating, right? If I get in a spaceship and fly the Andromeda Galaxy and fly back, I'm accelerating up to the speed of light, and then on the other end I have to turn around and come back, so I'm continuously changing my reference frames, whereas the twin at Earth stays in the same reference frame. So the consequence of that is that the moving twin traveling to a distant star system and back would age much, much, much less than the twin that stays at home. If I were to fly to the Andromeda Galaxy, 2.5 million or so light years away and back, about 5 million years would pass for people on Earth. And depending on how quickly I did that, maybe only a few weeks to months or years for me. So it's very interesting. If I could travel at the speed of light, I'd be there and back instantaneously, and still 5 million years would pass on Earth. So this is time dilation, a very weird effect of special relativity, but not the only one we'll be looking at in this chapter.